Hello and welcome back to the CCNA journey with me, Ryan, and in this section we're going to continue with IPv6 Part 3, focusing on EUI 64, Anycast and IPv6 Static Routing. It's worth noting this is another video taken over from the CCNA, so I may mention the CCNA or ICND1, but of course this is a pre-recorded video from that series. It's still all very relevant for the new CCNA. Now the video also assumes you know a bit about static routing, and if you're not sure about that, then watch it anyway, try to take as much as you can, and then there are other videos that are coming out for the CCNA that's going to dive much deeper into routing. And for those who don't know, you can contact me here on YouTube, on Facebook, LinkedIn or Twitter. So let's first have a discussion about EUI 64. Now EUI 64 stands for Extended Unique Identifier, and it's a method that allows a host to automatically assign itself a unique 64-bit IPv6 identifier without DHCP. Now it does this using something it already has assigned, which is unique, which of course is the MAC address. Now as we know, a MAC address is assigned by the manufacturer to the NIC card as it's manufactured. And because of that, we know that 9 out of 10 times that this is going to be a unique number, and therefore IPv6 extends that unique number and uses it for its IP address. And that's what EUI 64 allows. Now the thing with EUI 64 is it can be used on any address type, at least to an extent. So what do I mean by that is, remember in the previous videos we talked about global unicast. We said that that was used to route out onto the internet. Well, you can also allow the global unicast addresses to assign using EUI 64 the actual host portion of the address for everyone on the network. However, what it's primarily used for is the link local. Now remember, the link local is an address that is assigned to the interface, and it allows communication to happen locally on that segment. So we've got 10 PCs all connected to a switch, and they all get link local addresses. They can then communicate with one another because they're in the same broadcast domain, the same network, but they can't route out onto the internet because we can't go across that layer 3 boundary using a link local address. Now, the reason link local is primarily used with kind of EUI 64 is to save administration overhead. And the reason we rarely see sort of global unicast with EUI 64 is because of the security issues that come with that. Now, the security and so forth is way beyond the scope of the CCNA and ICND1, so I'm not going to get into that. Our main focus is to understand what EUI does, how it's used to kind of combat the overhead it saves the administrators without having to configure a DHCP pool, and how we would configure that using a link local address. So first of all, what we're going to do is take a MAC address from the lab, which I've got here, and we need to identify this MAC address, understand what it is we're looking at here, and then how we change it using EUI 64 to build an IPv6 address for us. Hopefully, if you're this fond of the studies, you understand a MAC address very well, but let's just recap very briefly on what it is we're looking at. So first of all, we need to know that a MAC address has 48 bits. Each of these double digits here are an individual byte. So we've got 1, 2, 3, 4, 5, 6. So that's 6 bytes. And of course, 6 times 8 is 48. We've got 48 bits. Now, we know that an IPv6 address is 128 bits long. When we're talking about these 64 interface identifiers and so forth, what we're actually talking about there is the host portion of the address, because the address is going to have a network portion and a host portion. So this is going to be something that kind of like your ISP assigned you, and then within this you're going to get 64 bits to play with. So that would be true if it was a global address. But it's important to know there's a network address, there's a network portion, host portion, 64 bits each. They can be different, just so you can in IPv4, you can in IPv6 extend the network to have less host bits and more network bits and so forth. But again, outside the scope of the CCNA for now, we're just concerned that 9 out of 10 times it's going to be 64-bit split, especially when you're using EUI 64, because as it implies, you can't do anything more or less than 64, which is kind of why this has become kind of like a standard, if you like. So here we know that we're focusing on the host portion, which is 64, and this is what we're trying to establish here, a method that host part of the address can be automatically assigned to a particular client. Okay, so we know about the MAC addresses, the bits and the bytes. The reason that's important is because in a minute we need to break up the MAC address, and we need to keep that fresh in our mind. So if the MAC address is 48 bits, but the host portion of the IPv6 is 64 bits, what do? How do we make up those missing bits? And it's pretty simple. We add FFFE into the middle of the MAC address. So it sounds a bit weird, but to show you what I mean, simply that. So we know straight away that FE80 means what? It's a link local. We can see the FFFE in the center of the MAC address, because notice we've got 000C, and then we've replaced all of our zeros with double colons, and then 0Z29. So there's the first part of the MAC address, FFFE, and then there's the last part of the MAC address. So now we have the full 64 bits. Straightforward, right? We took the MAC address and we popped in FFFE into the middle of the MAC address, FE80 at the front because it's a link local, and this is a IPv6 address that we can assign somewhere. Simple. Now, if you're thinking at this point, hang on a minute, Ryan, that address looks too small to be IPv6. Remember that the double colon represents a lot of zeros, and those zeros are what make up the full address. So keep that in mind. Now, the next part, now we've added the FFFE, is to do the flip bit. Now, this is the bit where the EUI 64 gets a little bit strange, but it's important that we understand it. So stick with me as we move on to the next part. So far we've got our MAC address and we've popped in FFFE into the middle of that to make our 64 bits. Now, for the second and final step, we need to invert the universal or local bit, and this is the 7th bit in the most significant byte. Now, when we use the terminology significant and least significant, we're talking about left to right. Because remember, when we type out decimal, the biggest numbers are kind of on the left, and we go to the smallest numbers on the right. Well, when we say most significant, we're talking about the highest on the left. So if we now get our MAC address and put it into the bytes, so we've got byte 1, 2, 3, 4, and so forth, this is our most significant byte. So this is where our tension sort of should be. And if we take that hexadecimal and put it into binary, we come up with our 8 bits, because each of those characters in hexadecimal represents 4 bits, and both characters represents 8 bits, which is of course a byte. So there's our 8 bits. And inside the most significant byte, we need to look for the 7th bit, or the second least significant bit, which is this person. And we need to flip it. So if it's a 1, you make it a 0, and if it's a 0, you make it a 1. So in this case, because it's 0, 0, we need to make the 7th bit a 1. Now we need to put it back into hexadecimal. So if we focus on the first 4 bits, we know that's 0. And if we look at these bits, Well, if we look at 0010 and we put it in our decimal conversion chart, we actually got 1, 2, 4, and 8. And to make sure we've got the right chart, if we actually add up all of these numbers, we will actually get 15, and we know F is the highest hexadecimal, which is 15. So we know that 2 is being flipped, so this 1 is actually a 2 in hexadecimal. So now if we change the MAC address back, the outcome is actually this. So notice that the second character in the first byte is now a 2, and then we need to put the FFE back into it. So our complete outcome is this. So there are 2 steps required then. The first one seems pretty simple. All we do is put FFFE into the center of the address to equal those 64 bits. Not a problem. The second, again, relatively straightforward. We just need to flip a bit. But actually, making sure that you know it's the most significant byte, which is the far left one, and remembering that is the 7th bit, going from left to right, which is this guy, and then being able to actually do the conversion from hex to binary, and then from binary to hex. And this is where the confusion comes in. However, with practice, it's relatively straightforward. All we need to remember is, of course, that each hexadecimal character is 4 bits, and we need to do the conversion from binary to hexadecimal. So here we are in a test environment, and you can see that this is the actual MAC address that we've been using in our sort of discussion so far. And we can see, as expected, it's actually the Burlington address for this NIC card on router 10 gig 1. And then what we're going to do is go ahead and enable IPv6 and have a look at which link local address is assigned to the interface and how it uses EUI 64. So let's get into the habit of, first of all, turning on IPv6 unicast routing. Even though it's not required for EUI 64, it's a good practice to get into because it's not enabled by default on iOS. And if you're enabling IPv6 and you're doing routing and so forth, then of course it needs to be enabled anyway. So that's now enabled, and then we're going to go to the interface, and we're actually going to just simply enable IPv6. And using the IPv6 Enable command, it goes off and builds a link local address, and by default it uses EUI 64. So we can straight away see that the FE80 has been assigned, and we can see the FFFE that's in the center there. But notice this here. We scroll up, we can see that the bit has been flipped as we would expect, and therefore that 0 becomes a 2. So just by doing IPv6 Enable on the interface, that basically says to the interface, I need you to come up as a link local address, and therefore you're going to get an FE80 address. And also part of that, I want to assign an IP address, and you're going to use EUI 64. So that's what the default is when we type IPv6 Enable. We can see things like the global unicast address is not configured, but we know from previous videos that you can have multiple IPv6 addresses on an interface. So if we wanted to enable a IPv6 global address, we can do that by going onto the interface and typing IPv6 address and then filling out the address we want. And then also we have the option at the end of that, instead of specifying the host portion, we can do EUI 64 as an actual command, and it will actually go off and do that for us. But IPv6 Enable by default will utilize EUI 64. So we've seen that in action now. We've seen that MAC address, just as we predicted in the slides, it added the FFFE to make the 64 bits, and then it flipped the 7th bit in the most significant byte. So Anycast is pretty straightforward. As we know in IPv6, we have unicast, multicast, and now we also have Anycast. Unlike IPv4, we do not have broadcast. Now Anycast is essentially a method that allows a particular user, let's say this user itself is based here, this user will use a Anycast address to reach a local server. So remember when we had discussions where we say multicast is one to many, broadcast is one to everyone? Well, Anycast is one to closest. So meaning that Anycast, you actually have multiple servers around the world, all configured with the same addresses, and using Anycast, it's able to identify the closest person or the closest server and then communicate with that server. Now I say this is new-ish in IPv6. It's newish in the sense of IPv6 recognizes it as an address type, and we as CCNA candidates need to be aware that Anycast is for IPv6. However, if we think about services such as 8.8.8.8 like Google's DNS and many other services, obviously it's not just one server around the world, there's multiple servers to which you can use 8.8.8.8. This is just a method that allows a PC or device to communicate with its closest server depending on where it is in the world. So a new address type that we need to be aware of that goes alongside multicast and unicast for IPv6. IPv6 static routing, very straightforward. It's just like IPv4. At least that's all we need to worry about at the CCNA level. So let's just jump into some Cisco's and configure some static routing for IPv6. So here we are back in the lab. We've got router 10 back, it's configured, and as we've done previously, all we've done on it was to enable unicast routing and enable IPv6 on the interface. I've also got router 9 here, so let's do the same with him. All done. Let's see if we can ping the link local address of router 10. So I'm going to go ping. I'm going to go over here and I'm just going to grab this address, paste it in, and let's see if we can ping it. So it's asking for my output interface. That might be because I didn't put a space there. And rightly so, that's why. There you go. So we're able to ping across to that link local interface now. Okay, so we've got reachability. On router 10, let's configure a loopback address and give it IPv6. Now we know if there's a loopback address, I'm going to have to route towards an address in order to get to the loopback address. So router 10 isn't going to advertise that to me, of course. So I need a static route on 9 to say if you want to get to the loopback on 10, go to the next hop of this link local address. So let's go ahead and do that. So IPv6 address, question mark it, is asking us for some details. Let's give it a global unicast address. So I'm going to give it 2001 colon FFFF colon EEE colon colon, and then we can just say that that's going to be let's put 1 there, 64 address. So all done. Let's have a look at the IPv6 interface brief. And we can see that there's a loopback address here configured. Obviously I don't have reachability to that at the moment. Let's just check that we can ping it local. We can. So I'm back at router 9. It looks like it's got timed out. And then we're going to look at, first of all, its IP routing table. And you can see we don't have a route, obviously, to that address that we've created. So let's create one to the loopback on router 10. So IPv6 and then we need to enter the address. So let's go back to 9. Let's go back to 10. Let's grab the actual whole range there. Pop that in. It's asking us which interface that we want to reuse, and of course the next hop. So let's type in the next hop address first. So that's going to be the actual interface link local address that I've configured. So not this one, because it's the link local address of the loopback, but this one up here. And then we can obviously put tracks and so forth, change the AD, things we've looked at in the past. Now, just like we saw with the pings, notice because we're using link local, we have to specify the next hop. So interesting, because obviously in IPv4, normally you can pop the interface on the end. In IPv6, we need to pop it in the middle. So let's just go back here. And then we're saying if you want to get to this 2001 IPv6 address, which is the loopback of 10, you need to go out of gig 1, and the FE80 is your next hop. Now, let's look at the routing table. Okay, we've got something in our routing table, and it's recursed because we've obviously given it the information we need. Now let's ping. And let's go back to router 10. And let's look at the interface brief over here. So it's important that you remember to type this IPv6 and all the commands. Easy to forget. And then we're going to grab this guy, go back, and we're going to say, can you ping it? Yep, I can ping it. So static routes work the same as IPv4. Very straightforward. You can set the next hop to the link local address, but if you do, you have to specify the interface, just as we've seen. I think if you do it to the global addresses and things, that's not required. I think it's only when it uses link local. But again, get in the lab, play with this, create some static routes, and ensure you're comfortable with how they look, how they work, and more importantly, you're comfortable with the EUI 64. Very surprised how quick we got through that, to be fair. A lot of information in this video. Just to recap what we went over, we first started looking at probably the most important topic in this video, which is EUI 64, the extended unique identifier. We talked about how it's used to sort of create the host portion of an IPv6 address. We said that that's the 64 bits. We said that the MAC address that the manufacturer puts on the NIC card is used to create that unique address, and it does that by popping FFFE in the middle, and that takes it from those 48 bits to the 64 bits that we need, and then the 7th bit. So again, this is where a lot of people get confused by this, but in the most significant byte, we take the 7th bit and we flip it. If it's a 0, it becomes a 1. If it's a 1, it becomes a 0. And when we move it back to hexadecimal. So we might want to practice a few times there. Maybe go on Packet Tracer, GNS3, or some real equipment. Look at the MAC address. Work out what you think the EUI is going to be. And then, just as we've done in the lab, do the IPv6 Enable. And it will create a link local using the EUI 64 technique. We had a brief discussion on Anycast. There's not really much to it. It means one to closest. Multicast is one to many. Broadcast is one to all. So Anycast is a new sort of address range that's been brought into IPv6. And as we know, broadcast has been removed from IPv6. And then static routing, we jumped onto the lab, had a bit of a hiccup because I didn't put the next interface. I forgot that it had to do the recursion for a link local address manually. But again, didn't want to edit that out, wanted to show you the mistake so you can see it. And so it's important that you get on the lab and you actually encounter these mistakes yourself, because that's how you learn. And of course, create some static routes so you're comfortable with that. I hope this video has been informative, and I'd like to thank you for viewing. And if it has been, please do like and subscribe.